Hello everyone, and welcome to this session where we will use the structural analysis program Ftool to analyze the statically indeterminate composite structure shown in the figure on screen. A composite structure consists of a combination of axially loaded members as well as members subjected to bending. In the figure shown on screen, beam ABCD is supported by a hinge at A and two cables at B and C. The problem under consideration is stated using the United States customary system of units. It is required to find the support reactions and the tension in the cables. Then we are to draw the shear force and bending moment diagrams for the beam. I will briefly explain the hand solution using the consistent deformation method and the virtual work method before I solve the problem using Ftool. By drawing the free body diagram of the beam alone, we realize that there are four unknowns, which are the two reactions at A, the tension in the cable at B, and the tension in the cable at C. On the other hand, we only have three equations of equilibrium, which renders the problem statically indeterminate to the first degree. The problem can be solved using a combination of the consistent deformation method and the virtual work method as stated earlier, and it can also be solved using Castigliano's least work method. In the consistent deformation method, the force in one of the cables is selected as the redundant. A primary structure and a secondary structure are then drawn. Then the compatibility equation is written to find the redundant. Remember that the virtual work formula here has two parts, the integration part pertaining to the flexural member and the summation part pertaining to the cables, which are treated here as axially loaded members that only carry tension. I will now demonstrate the solution procedure using the computer program. After performing structural analysis of the composite structure, I will ask the program to display the reactions, then draw the shear force and bending moment diagrams of the beam, as well as the deformed shape of the structure. Note that the question gave us the cross-sectional area of the cables and the moment of inertia of the beam. In the absence of any other given information, we will assume that the beam and the cables are made from the same material so that the modulus of elasticity will cancel out in the hand solution. In the computer solution, though, we will have to assume a certain value for the modulus of elasticity for all members in order for the program to perform the required analysis. We will now initiate our Ftool session. By clicking on File, Open, we can load the United States customary units template that we have created in previous sessions. If you have not watched the previous sessions, then I encourage you to do so in order to keep up. By looking at the question, we will need to define an origin, which will be at point A. So point A will have coordinates of 0, 0. And we will have to create nodes at 10 and 0, 20 and 0, 30 and 0. For the cables at the top, we will have a node at 10, 10, and at 20 and 10. Let's do that here. I'm gonna activate the keyboard mode, click on Insert Node, and insert these nodes one by one. I need one at the origin, then at 10, 20, 30. Then I'm going to need one at 10 and 10, and another at 20 and 10. These are our nodes. I'm going to deactivate the keyboard mode and click on the Insert Member button to start inserting my members. This here is the first segment of the beam, the second, and the third. And this here is a cable, and this here is another cable. Note that at this particular stage, we are just defining the geometry. We are connecting nodes to form members. We are not actually specifying whether these members are beams or axially loaded members. We will do that at a later stage. The next step, we will have to assign a material property to these structural elements. So I'm going to click here on material properties. I've already created a material and called it material number 1 in previous sessions and previous examples. So I'm just going to use whatever values are inserted in the previous examples here. I'm going to select all my structural elements and assign material number 1 to these structural elements. The next step is to assign cross-sectional properties. I'm going to define two cross-sections here, cross-section 1 and cross-section 2. Again, if you do not know how to define these cross-sections, then I do encourage you to go back and watch the previously recorded sessions in order to keep up. In the first section, if we look here at the question, we will see that the beam has a modulus of elasticity of 576 inches to the 4, while the cables have a cross-sectional area of 0.1 inch to the 2. Let's start with the beam element. I'm going to select here all my beam segments, and in section number 1 I'm going to insert the value for the moment of inertia, which is 576 inch to the 4, and I'm going to apply a very large value here to the cross-sectional area in order to prevent any axial deformations in the beam element. Next, I'm going to assign these properties to the selected members. So there goes my cross-section for the beam. The next step, I'm going to go here to section 2, select these two axially loaded members, and define a cross-sectional area for these axial members as 0.1 inch to the 2. And I'm going to assign a very large value for the moment of inertia in order to prevent any flexural deformations in these axially loaded members. Next, I'm going to assign this cross-section to the selected members. The next step is to define our supports. If we look at the question here, we will see that there's a pin at A, and there are two supports that hold the cables in place. So I'm going to go to supports, define a pin support here, and assign it directly to the first node on the left. Now, the types of supports introduced here are irrelevant, because we will see later on that we will define these members as pin connected members. So I'm just going to need a support here to hold them in place. So I'm going to assign the same pin that we've created here to these nodes, but I'm going to rotate the angle to 180 to have these supports look nice on screen, and I'm going to click on assign. The next step, which is very important here, is to go to this button here in order to select these two axially loaded members and actually define them here in the program as pin connected members. So I'm going to go here and tell Ftool that the members on screen are actually members that are pin connected at both ends. And I'm going to assign that to these two members. You can see that immediately the command is reflected on screen, and these two members now are nothing but two force members, and in particular they take only tension forces because they are cables. The next step is to define our loads. We have a concentrated load as shown here at point D, which is 10 kips. So I'm going to go here to concentrated loads. I've already defined the load with its magnitude and direction. I'm going to assign it to this particular node here as 10 kips. So now we have drawn our geometry, we have assigned our materials, we have assigned our cross-sectional properties, we have introduced our supports, we have introduced our rotational releases or boundary conditions in terms of the members that are pin connected. Then we introduced our load, and now we are ready to run the program. In order to check the axial force diagram, we can click here on this button. You can see immediately that the axial force diagram is drawn for this member here and this member here, which are axially loaded members, whereas no axial force diagram is drawn for the beam. As you remember, we eliminated any axial deformations in the beam, and therefore the axial force diagram is drawn only for the pin connected members. If you reduce the scale here of the axial force diagram, then you can see the internal force in each of these axially loaded members. And you can see here that I've already introduced the reactions. If you want to hide the reactions, then you can click here and remove them. And if you want to show the reactions, then make sure to hit the one that says reactions with values to see the arrows and the reaction magnitudes right next to them. If we want to check the shear force diagram, we can click on this button here. You can see that the shear force diagram is drawn only for the flexural member, which is the beam. These two here are axially loaded members, and thus they will have no shear force diagrams. And if we click on the bending moment diagram icon here, we can draw the bending moment diagram for the beam element. If you want to check the deflected shape or the deformed shape of the structure, then you can click on this icon here. When we click on this icon, we will see the deformation that occurred on screen. I want you to pay attention here to the fact that this axially loaded member here will stretch. It will suffer from an increase in length. And remember that the increase in length is proportional to the magnitude of the force acting on the structural element. So this member here carries a larger axial force, which is 14.625 kips, and thus it will suffer from a larger increase in length or a stretch, whereas this axially loaded element here is carrying a force of 0.75 kips, and thus the stretch that happens to it is much smaller. If we can increase the scale from here, you can see that. And I'm going to reduce the scale of the entire thing. So you can see here that this axially loaded member suffers from a huge stretch here due to the force or the magnitude of the force, which is large compared, very large compared to this one here, which suffers from a smaller amount of a stretch or increase in length. If you actually increase the scale of the deformed shape, you will see here that the beam actually here has an upward displacement before it has a downward displacement after this point. This concludes this session. Thank you very much for being with me, and I hope that I will see you in future sessions. Best wishes.